get the recording going again. So how are you guys doing with this? Are you up to speed on Dirac? I hope, even if you're still tidying up the final bits of that scalar field stuff, I hope you'll do the exercises in the Dirac field section just to make sure you're up with the notation. Let's see. So let's see, we were talking about projections, right? We did the energy projections. Did we do the spin projections yet?
Ooh, I don't remember.
I may have started those. Yeah, sounds off, Alex. What were you saying?
I was checking, sorry, but I think that's right. I think we just I think you wrote down that how they form the identity operator on the full space, the spin and the positive energy projections.
Yeah. Okay. Yeah, I do remember that now. That's right. I introduced two different spin projections. One is helicity, which is not Lorentz invariant. Neither of them fully commutes with the energy projection, but if the forward momentum and the forward spin vector are orthogonal, then the P commutes with the spin operator. So that's what we need. We want spin to be a space-like vector. And so, somebody filled the board, just a second. Yeah. Somebody was using this board for a different class. So I hope those of you in quantum paid attention to the time ordering operator, because we need it here. Okay, so the operators, we've got the energy projection operators, and we can write those as a half of the identity plus or minus, and then basically it's P slash 1 over M P slash, right? Yeah, that's right. Then for the spin, I call it pi plus or minus. We have 1/2, 1 plus or minus, and then we need a gamma 5. And which side? Yeah. So there's an S slash gamma 5, where S and P are orthogonal, and S is a unit space-like vector, so it has norm -1. And now that spin projection projects out, right? If we project by energy, that gives us the first two components or the last two components of our spinors. It gives us the U's or the V's. Among the U's, U1 projects as a spin up, U2 as a spin down component. Among the V's, V2 is the spin up, V1 is the spin down. And all of that follows necessarily from being able to diagonalize both spin and energy at the same time, and because of the trace-free character of the spinor metric. So now we can write the full. Hang on here. Let's see. Have I written the full solution to the Dirac equation yet? Let me see where I might have here in the notes. Oh yeah. Psi and psi bar. So psi looks like this. Okay, there are our operators. We did work through those. Now, psi itself, it's like this. So we need 1 over 2 pi. This is our usual Fourier coefficient. We're going to have a sum I equals 1 to 2 over the spin up and spin down states. Then we have an integral over 4 vector wave amplitudes, then a normalization m over omega. And now we have a Dirac delta function selecting the positive energy states, and those have to be expanded with the u's. For each different spin and each different wave vector, we have an amplitude. So this depends on k and omega. And then we have a basis spinner, which depends on the for momentum. Yeah, I could write, well, let me write it this way. P depends on P, then the basis spinners, and then the Fourier mode, and that's the usual minus I P alpha X alpha. Then we have the negative energy states where E has to be equal to minus omega. And we have some conjugate amplitudes here. And the negative energy basis spinners and an I P alpha X alpha, close paren. So there's a full solution to the Dirac equation. And then, of course, we do the energy integrals. And I'm going to skip down to where I do that. So we're going to do all the same things that we did for the scalar fields, right? We're going to, okay, we do the energy integrals. That fixes the omega to be given in terms of the k. So we really only need to write these mode amplitudes in terms of the spatial part of k. And then we're going to invert and find the solution for those mode amplitudes in terms of the fields. And then that way, when we quantize the field and impose canonical quantization conditions on psi and its conjugate momentum, it induces operator status onto the B and the D, which are going to annihilate a particle or create an antiparticle. This becomes a dagger. Now, notice we have a whole extra space going on here, right? These are complex 4 vectors, each of these basis spinners. You know, once you specify the momentum, those are fixed orthonormal basis in that spinner space. The linear combinations are these coefficients. So for each momentum, we have a well-defined set of basis spinners, and we can introduce each one with a different amplitude. So these guys are the amplitudes, and these are the only freedom in this expression, right? They're the things that have to become operators. So carrying out the integration, let's see. Oh, well, I'm not sure I actually wrote this in the notes. Maybe I should write this in the notes, but let's put it here. Sum I equals 1 to 2. So we get down to D3K, and then this is omega K. This is the square root of K squared plus M squared. And now we've done this energy. So this becomes VI of, we can write it as just K here, UI of vector K, E to the minus I omega t minus k dot x. And then the second one becomes still the conjugate, just depends on k. Spinner just depends on a 3 vector. And then here we have e to the, okay, we have e to the plus I omega, so plus I omega t minus kx, except the energy is negative. So now we get minus I omega t, but then this will be minus, wait a minute. All right. Let me do it in 2 steps. E t minus k dot x. There's the inner product, but e is minus omega, so I can pull out a minus here and a minus there. So it's omega t plus kx, where omega is always positive. And then we want to take the, we want to find psi of q by taking the, at time 0, we can find the Fourier transform of the spatial wave function. So we're going to take d3k, oops, d3x, then psi of x, e to the, I think it's now, I always have to check. Every time I write a Fourier transform, I'm going back and checking whether I need to be multiplying by e to the plus or e to the minus the iq dot x. So, excuse me. Yeah, that's going to work because, so here we have plus k, we're going to have minus q, so we'll get a, when we integrate over x, we're going to get a delta, a Dirac delta of k minus q here, and then down here we'll get a Dirac delta of k plus q. So now I know some of you spent, I don't know, how many pages did it take you guys to do this for the scalar field? I might try to do it. Yeah, 5?
A lot.
A lot, yeah, yeah, I know. Been there. You know, watching you guys write out 15 or 20 pages for this problem is bringing back fond memories to me because, you know, I remember spending days and days, you know, doing these long field theory calculations when I took the class, and they're long. They get a little faster. Yeah, 17 pages. Guillermo, and yeah, I think yeah, I don't know. I think Lyle may be rapidly gaining on you there. So there's more come. Let's see. So how many of you have finished that and sent it to me? I have to tally up. Okay, so yeah, I've got a couple in. You know, finish it up. You know, do it all. You know, it's good for you, right?
It's good for the soul.
Yes, right. Yes, your physics soul will love you. You know, that I really do want you to carefully work through the Hamiltonian particularly, because, you know, getting the right signs there so that, you know, 2 of the terms give 0 and 2 of the terms you get a factor of 2m or something, or, you know, some simple factor like that. And, you know, if you don't have your signs right all the way through, then you're going to have, you know, 1 term's an m squared, 1 term's a k squared, 1 term is an omega squared, and you have to have the right relative signs for those to either satisfy the energy condition or give you twice the energy, right? And so, you know, getting that to work out yields some well-deserved satisfaction by the time you're done. Okay, so yes. You got it, Lyle. Yes, eat our vegetables, exercise, solve QFT problems. You know, this is the route to the good life. Okay, well, but you guys know that, right? You're here for a reason. Okay, so Whoops.
I did want to ask a quick question.
Oh yeah, please.
So we just integrated the time coordinate away. Were there any, is this still pretty general, or were there any assumptions we had to make in order to do that?
No assumption.
Okay.
Right, in order to satisfy the Dirac equation, that the usual classical energy condition has to be satisfied. So E squared equals K squared plus M squared. Right, that was a consequence of the Dirac equation. That leads us to put in either delta for positive or negative energies. That's what guarantees the Dirac equation is satisfied. But then in each of those cases, we found there were two possible independent spinners. Right, so this is completely general. This is a full solution to the free Dirac equation. And then since we have a couple Dirac deltas, we can just do that integral. Hey, Eli, how you doing? Have a good weekend? Yeah, okay, good. Yeah, I hope, yeah, get outside. You know, this weather, it's supposed to hit 60 by the end of the week. Oh, yeah, so go for a hike, you know, get some fresh air. It's hinting at springtime. Okay, so we want to do the x integral. We've got this exponential is going to combine with the kx. I'm setting t to 0 here. We're just looking on a time slice. This will give us initial conditions, and then the rest evolves in time. But you know, according to the energy. But now this first one is going to be e to the minus I q dot x plus I k dot x. So the x integral is going to give us a del 3 of k minus q. All right, and then let's see. Hang on. Let me put in the d3k and the normalization here, m over omega, and now everywhere omega depends on k. So we have bi of k, ui of k, and now we're going to get a delta of k minus q here. And then on this term, we have a minus k and a minus q. So for the V-type fields, we're going to have del 3 of k plus q. K plus q like that. And I got it all on one line. That's always nice.
Hey, Dr. Wheeler, what happened to the summation over I when you do the transform?
Oh, still there. It's still there. So we have both spins here. So yeah, always we have the sum over I. And then now we do the wait a second. What happened? We got Dirac deltas. That gives us a 2 pi cubed. So we end up with plus 2 pi. Why did I have? Oh. Sorry. There's a 1 over 2 pi cubed here, but also this Fourier transform. Sorry, this has a 1 over 2 pi cubed to the 3/2. I always put a square root with each Fourier transform or each inverse Fourier transform. So psi comes in with that factor, and then the inverse transform comes in with the same factor, gives us 1 over 2 pi cubed, but then the delta function comes in with a 2 pi cubed, and they cancel. So then we can do this last integral, and we're going to have a sum over I, bi of, now it'll be q here, ui of q, plus di conjugate of minus q, vi of minus q. like that. So we're halfway to a solution now. Let's see, do we just get to take we can just take the dagger of all this to get the adjoint. So psi dagger, this is on the way to giving us pi. So now we get b dagger of q, ui dagger of q, plus di unconjugate vi dagger. So you can see we're going to have to figure out, what is vi of minus q, and there's a simple relation for that. Then let me see. So yeah, we're going to want to solve for this, but we need pi. Pi is given by psi dagger. What is the expression I have here? I psi dagger h gamma 0. Like that. And that's all right, h gamma 0. All right, those basically square to 1, but the h lowers an index. So pi actually has the spinor index down if we wanted to write the spinor indices, which every now and then it's a good idea to do. Okay, so now in order to sort this out, we need
There's
a
a
bunch.
question from the chat.
Yeah, question. What we got? Oh, should the complex D be a dagger in the third to last line? Not yet, because we haven't made these into operators yet. Okay, it's, this is just a Fourier expansion of some complex field, a spinor field at this point. But if we take, right, a spinor has a dagger because you can take the transpose of the spinor. But these are just functions. D is just a complex function. It's just the amplitude for each mode. So, no, and this is a confusion that I have fixed this in the current edit of these notes. When to put daggers, when to put complex conjugates. So I do everything I can in the classical field theory in the notes now, which includes solving for these mode amplitudes. You can do that entirely classically before you quantize anything. And then this is a thing I worried about when I was, first working up these notes and working in field theory was, is there any other way to quantize a field than by quantizing the mode amplitudes? The answer is no, there's no other freedom here, right? All of these things these are just some basis spinors. You're not gonna turn the exponential into an operator. In fact, you can solve for these functions entirely in terms of the original fields, psi and pi. And that means that when psi and pi become operators, those guys necessarily become operators too. So it will be B and D that get hats on them. And at that point, this D becomes a dagger. Now it becomes, think matrix, right? It becomes an operator. And so the dagger is now a meaningful operation. So it's a great question. It's something I, worried about a lot initially, but, we're doing it right here. So what we need, we can't just add and subtract these things now, right? With the scalar field, one of these was this plus that, the other was that minus that, but there weren't these basis spinors. So we have to use properties like the orthogonality of the spinors in order to, bring a spinor in on one side of these guys in order to extricate these expressions from the spinors, so that when we add and subtract these, something cancels and something adds in a way that we can actually solve for B and D. So that becomes not really, well, not really trivial, but not really non-trivial. We're just we're taking some inner products with some vectors. It's just that with these new basis vectors, it's not I hat, j hat, k hat, 1, 0, 0, 0. Now there are all these non-trivial components that depend on the momentum. Well, okay, so one thing we could do, which is not really cheating, is to say, okay, let's look in the rest frame, because this is all Lorentz covariant. Let's look in the rest frame and use the orthogonality properties we find there, and then say, okay, now boost to whatever frame you like, and those things still have to hold. That's absolutely true, but curiously unsatisfying. It's nice to actually look at the components of these spinors and see that they really do the orthogonality things we need. So what do I want to do? I want to keep sort of every other line here. We don't need this stuff right in the middle here. And so what I've tried to do, that again is different from most of what you'll see, is work with a spinor inner product, which is defined by the dagger of the first and our spinor metric and psi. In components, that would be chi dagger A, HAB, psi B. So this is our inner product on spinors. Sorry, my voice is getting a little raspy here from talking all morning. Okay, so what do we want to do? Let's look at what V of minus K looks like, because we actually have to deal with this minus sign in V. And what else? Sorry, we just need to get rid of our solution here too, so we have some place to work. Okay, so that's our spinor inner product. Now V, let's say V1, we've got this normalization m plus omega over 2m. And then, what I want here is V of minus K. So referring back, but I'm just going to copy from what I've written here. We have Kz over m plus omega, Kx, which way does it go, plus IKY. And then 1, 0. Okay, and what that is, if I pull out a minus sign, these become plus, so they go back to V of plus K. This one goes to minus. Now, if you remember, gamma 0 is 1, 1, minus 1, minus 1. So I can fix the minus sign here in these last two components, basically, by multiplying by a gamma 0. So if I write minus gamma 0 V1 of plus K, it's the same thing. So this minus sign changes everything to a minus, then the gamma 0 puts this back to a plus, and we have V of plus K. And the same is true for V2. I'll just write that one. So V2 of minus K is minus gamma 0 V2 of K. Same thing happens. The only difference in V2 is that basically these are interchanged and there might be some signs. I think it's a conjugate. Yeah. So this one is this is the first component, but it's the conjugate here. And this is the second component. but everything changes sign the same way. So that gives us a way to write the v of minus k in terms of v of k. Now, probably as an exercise, I've had you compute inner products. Oh, there's a typo of the u's and the v's. And they're the following. So the inner product of ui with uj, all right, is, why do I have v? Yeah, that should be another. So this is chronic for ij. Those two are just plain orthonormal. If I take a u with a v, either u with either v, I get 0. Those are orthogonal. And then this curious property of the indefinite metric, we get minus delta ij for the v's. And I'm pretty sure that you've all already shown that in the exercises, right? Because you're all right up with the reading and hanging on every line here. Yeah, okay, good. I know, but get there. So, do those proofs. It's just a dot product of two vectors, right? So, those aren't going to take you long. You can do it by inspection, but do it. Just, see that those things are actually orthonormal. Helps to write out a few components. And, the dot products of, stuff like this with itself, you're going to get k squared stuff. And here you get a 1 plus a k squared over m plus omega squared with this normalization squared. You have to use the energy, omega squared is k squared plus m squared to sort that all out. It works out, but see that it works out. Okay, we also are going to need v bar, but that's not too hard. Let's see. Okay, so v bar is v dagger h, and let's see. Oh, but yeah, we're gonna have v bar at minus k. So that's a v dagger of minus k. But now that's minus, where'd it go? Let's see, I can put this gamma 0 on either side. It's a diagonal matrix. So I can write v dagger gamma 0 h if you like.
So you're missing an h in the middle term of that equation, right?
What do I have?
You had it and then you erased it. There's an missing h factor in the middle term of the equality.
Oh. Yeah, okay. Yeah, let me do this more carefully. Let's see, right? V bar is v dagger h. And v dagger of minus k, right? We take the dagger of that expression over there. So that's going to be v of k dagger. The gamma 0 flips to the other side. We get a minus sign, and then the h is still there. So there we go. That's the expression. So that lets us write v bar of minus k in terms of v of k. Oh, let's see. Okay, then I give another exercise. The inner products, all right, so you will have already shown by the time you're down reading this part that these inner products hold, but we need some other inner products because they come up when we're working with expressions like this. So it will help to have the following. If I have uj with gamma 0 ui. So So if one of these, this is still another spinner. Again, it's just a matrix times a spinner gives another spinner. That inner product picks up a factor. This is the definition. All right, this is going to be uj dagger with an H with a gamma 0 and a UI. And it turns out to be just a factor times Kronecker. So we get omega over m times delta ij here. And similarly, for a couple of V's, if we have VI with gamma 0 Vj, and I forget whether, I don't think we need the U with the V, in fact. And I'm not sure it is 0, but this also turns out to be what I have written here is plus omega over m delta ij. So that could be because this gamma 0 puts in an extra minus sign, and so could make it positive. Okay, so now we're in a position to isolate the mode amplitudes. So we're going to use these products. Let's see. So psi, okay, BU minus D star. I have a tilde on these things. Why do I have a tilde? Just because it's the Fourier transform. Anyway, here, I wonder if that's supposed to be a bar. I should check my notation here. But what we can do is, right, this is a V of Q using this form here. So we need a minus gamma 0 here. So let me put that in. So this is going to become a minus. And then we have gamma 0 V of Q now, the I of Q. We got the minus, change the sign, put a gamma 0. And that's just a function still. So now we do the same for this one. And V dagger, we've got that here. So that's still going to be a dagger, but we get a gamma 0 H over here. The minus sign goes away, and we get an overall minus here. So that turns those formulas into, so we now have spinners at positive thing, but notice we've pulled in a gamma 0 in certain places. And then pi, let's see, all right. This is going to be, all right, we have an I out front. We have the sum on spins. And then psi dagger, and then we need an H gamma 0. So
I'm able to see what's going on.
Yeah. Yeah, okay. Thank you. Okay, so yeah, I'm just multiplying this out. So we need an H gamma 0 on the psi dagger equation. So I've got the I here. So we're going to have BI conjugate, right? The I conjugate, and then UI dagger with an H gamma 0. So UI dagger H is what we call U bar. And then here, these guys go away. So we just get a VI dagger, but then of Q. But bringing in an H gamma 0, H squares to 1, gamma 0 squares to 1. That may actually be an H inverse here, but they're the same matrix. If you carefully work through the index positions, this will be right. But now we're in a position to look at the what projection on psi and pi is going to isolate something over here. And so I have to consult my notes to see what that is. Oh, now wait a minute. There's an H gamma 0. Something's different than, yeah, maybe that was supposed to be a psi bar. Okay. Yeah. Psi dagger H gamma 0. Yeah, maybe this is bar. Yeah, my notes don't have an H here. And I know I checked that a number of times, but it depends whether you're talking about, psi or psi bar. A bar means you've got an H on it. Otherwise, you just have psi dagger. So let's see. So U dagger H gamma 0. So this term's right, but yeah, I must have been acting on the barred V. So if this is barred, then we haven't. All right. All right. Plane pi should be B conjugate U bar. Oh, okay. So yeah, let me write out the pi of Q. All right, so pi should be I square root of omega over m. And then we should have a B conjugate U bar. And then the V part should be D and V bar minus, DI V bar I, both of minus K. Oh boy. And then there's an overall gamma 0. Okay, so that's the correct expression for pi. But now we want to replace this V of minus K. So let me double check that. Yeah, that's going to insert another gamma 0. So the first part is the same. Okay, and now we're going to get oh, this was a plus. Okay, so this is a minus. Good. So we're going to still have DI conjugate of minus K. But now this is going to be V of plus K. And now let's sort out the H's and gamma 0s. So what's going to happen is we the V dagger, in order to change it to plus K, we need a gamma 0. Because it was barred here, we have an H. And then we have a gamma 0 out here, so that gamma 0, that H is actually nested between two gamma 0s. All right, but that in fact brings us back to H. So gamma 0 is on both sides. Even a transpose, gamma 0 is diagonal. So the minus signs are going to cancel and you get back to H. So the conjugate momentum, finally, we can write as B star of K, UI bar of K, minus DI star of minus K. And then this all becomes an H. So was that a V dagger? Yeah, that was a V dagger. Jeez. Okay. Yeah. V bar is V dagger H. So this is V dagger, but gamma 0 because we're changing the minus K. So gamma 0 H. And then the extra gamma 0 here. Those all become an H. So this just becomes a V bar of K. Wow. Okay. So you guys have my sympathies when you try to do these theorems. You know, it's just, yeah. Bored. Okay. So questions. How about it? Anything? Okay. Okay. So, you know, it's, yes, it's harder to do this on the board than it is on paper. It's bad enough. It's bad enough, you know, working in licks and writing these things correctly. So now, if we take the inner product of U with gamma 0 psi, geez, wish I knew what psi tilde was. I think I just mean the conjugate field. Gamma 0, because what am I writing? D of minus K and V. So, yeah. So if I take the inner product of this one, with a gamma 0 and a U. So the inner product I want to take is UI of K with, I think it's gamma 0 psi. Let me double check, yeah. Gamma 0 psi, or I guess we're talking about Q here. Q. Okay, so so what happens? So I multiply this by gamma 0 on the left. So what happens is that squares away this gamma 0, and it means I'm taking the inner product of U with V. So this term is going to give me 0. That's why I put the gamma 0 here, to make sure that term goes away. So then what I end up with is the sum on I, bi of Q, and the inner product of U, I, change the dummy index here with gamma 0 uj, all of Q. And now we work this one out. Let's see. Have I forgotten a normalization? Yeah, all this is root omega over m, I think. Yep. No, m over omega. Jeez. Okay. So feel free to be as critical of my presentation as you like once you've done these two. Okay, you know, I know I'm all over the place here, forgetting things. You know, maybe as young and as astute as you all are, you'll just whip through these. But yeah, we'll see. We'll see. Yeah, there are just a lot of things to keep track of. Okay, so we have a sum we have root m over omega. But the cool thing is with the gamma 0 in here, that inner product is the square root of omega over m, so it cancels that. And what we get is just bi. So we actually totally exactly solve for b. And no, we don't. Wait, why is there an omega? Why doesn't that cancel? Oh, rats. Okay, it either cancels or it doesn't. There may still be a factor of m over omega here. Oh, there's the problem. Okay, I see it. I wrote these. Okay, ui with gamma 0 uj is omega over m, not the square root. That's the problem. So we end up with the square root of omega over m here. In writing up these notes, I did all this 3 times. You know, I did it with the initial normalization that I had, and by the end, the normalization of my B and my B dagger had some constant in it. And so I went back and I put a different normalization for these things. So it turns out that what I've got are the right normalizations, so that by the time you get to the end, the commutator of B dagger with B is delta, not something times delta. So yeah, the reason for all of these factors in front is, well, to make them correct in terms of whatever you start with, but it's also so that by the end, you get down to the right thing, to the simple commutation relationship you really want. So the upshot of all this is that we can write Bj of Q as root m over omega times the inner product of ui with gamma 0 psi. So think kindly, because I could have just written that in the end and said, do that as an exercise, and left you all of the details here. I may have done that. Actually, I work out all of these, so it's in the notes and you can read about it. You do a similar thing to isolate B dagger and D dagger. So let me just write the final results of all that. Before I erase anything, are there any questions on the general procedure here, or any details that I can clarify? Yeah, okay. So following through on this sort of solution, we find Bi dagger, we find Di, and Di dagger of Q. Or is it a minus? Let me see what I end up with. Now the D's end up at some, so you get an expression for D of minus K in terms of size and things, but then you can just change K to minus K everywhere, and now you have D expressed in terms of other things of minus K. So in the end, we get B dagger is minus I. Everything has a root m over omega in it. And this is V of minus K, psi of minus K. Well, or K or Q, whatever. Okay, that's, wait a minute, which one's that? That's D dagger. Sorry. D dagger. So now one of these is D, this will be B dagger. Okay, B daggers. No, I. Sorry, lost track of which line I was on. This one's got a minus I. But a simpler inner product. B daggers pi of k, u of k. Going back and forth between K and Q here. I guess I ended up with K is now D is minus M over omega and V with psi. Uh-oh. That's D dagger. Pi with gamma 0 V.
So each amplitude, if you will, differs by a factor of I. Huh?
Sorry, say again.
Maybe not. I was hoping to see that every term would differ by a factor of I.
D. Yeah, 2 of them are negative, 2 of them have I's. Equation 6.17 gives these. I'm just copying those. So pi of minus k gamma 0 v of minus k. Okay, so I think I've got these right now. So is there a question? Does something not match?
No, that matches my intuition for sure. I wanted to see each one have a factor of I. There are 90 degrees out of phase in the complex plane.
Yeah, so these are 90 degrees out with those. That's right. Yeah. Okay, so we've solved for the mode amplitudes. So now we can pretty much put hats on everything and work out the commutation relations. Canonical quantization. We're doing the same thing we did for like the simple harmonic oscillator here, only its fields and they're long. Let's see. So I've erased my solutions for the fields, but put hats on everything. And it's B and D that gets hats and become operators, and complex conjugates now become daggers. And we impose canonical commutation relations on psi and pi. So psi A with pi B. And these are equal time commutation relations. So X and T, and this will be Y and the same time T. And so we've got to be talking about the same components, psi A, B. And we're going to get our I H bar, where H bar is 1. And then we get del 3 of X minus Y. Like that. So canonical commutation relationship between the field and its conjugate momentum. Okay, so you can write this as what turns out to be a little easier. Instead of pi, you can write psi. Wait, do I write psi bar or dagger? Yeah, and psi dagger of Y. Now these have all become operators. So Dirac rules because Dirac rules. And we can do that with just a gamma 0. The I takes care of itself, I believe. If my notes are right here, we get a delta AB and a Dirac delta, x minus y. So we have expressions for psi dagger as well. So that's potentially handy to work out. Then, let's see, are there other versions? No, I just wrote that in components. So let's see. In terms of operators, okay, so we have these inner products. I'm not going to write all these out, but you know, explicitly in terms of the fields. Let me just write the first one so you can see. So bi hat of k is in detail 2 pi to the 3 halves. Sum on, oh no, I'm sorry, i's free. Root m over omega. Integral d3x of u, ui, now an operator of k, and gamma 0 psi hat. And finally, a Fourier mode e to the minus ik dot x. Like that. Okay, so you can write very explicitly all the B's and D's and B daggers and D daggers, and those are, I've written those out in terms of the fields and the basis spinners. Okay, so now the next step is to compute the commutation relations. And here it goes wrong. B with B dagger goes very much as you would expect. B with B dagger, once I sorted out the normalizations by working it through multiple times, what we find is that B with B dagger is 1 with suitable Kronecker kinds of things. So concretely, the commutator of Bi of k with Bi dagger of q. Now operators, I and j. You get Kronecker ij. So a spin up commutes with a spin down, no problem. And then you get del 3 of k minus q. And let me not try to put this calculation on the board because I'll just go crazy. But this one, the D with D dagger, read through the notes. I do it 2 different ways, right? I do it in detail with all the fields written out. I do it with psi and psi dagger, and I do it with psi and pi, just to confirm that there's no mistake. But the upshot of all that after about a page is that di of k with dj hat dagger of q is, you ready, minus delta ij Dirac delta k minus q. So it boils down just right, but I promise you there is a sign, and you can't get rid of that sign. There's almost no option at all for getting rid of that sign. It comes from, well, in part it comes from the tracelessness of H, the particular form of the inner product that you need on these spinors in order to be able to construct real vectors from the spinors. And so I did that the easy way. I did it a fairly convoluted way, and you can read that. So question is, how do we fix it? And this is very cool, and this is the reason that I did it two ways, and that I very carefully introduced the spinor metric to, see what could be done with that. I see no way around this other than requiring the fundamental commutators to be anti-commutators. That introduces one more sign just where you need it. So instead of this, we make this an anti-commutator. And all of these become anti-commutators. And what happens down here, by the time you follow through, is that that sign goes away and you've done no other damage anywhere. So this is a new rule that we are forced to introduce beyond normal ordering. So if we have operator products and we have to interchange like a B and a B dagger. Okay, so we've got normal order of B dagger, right? Okay, you're gonna write B dagger B, but you're also interchanging two fermion fields. You get a minus sign. So the normal ordered product of B dagger is minus B dagger B. Every time you interchange spinor fields, you introduce a sign. And that is the exclusion principle, remarkably inescapable. The fact that we anti-commute spinor fields, psi 1, psi 2, right? Those anti-commute. So if that means that psi 1, psi 2 is minus psi 2, psi 1. If I try to write psi 1 squared, psi 1 squared has to be minus psi 1 squared, so it's got to be 0. So fermion fields square to 0, which means we cannot have two in the same state. If they're identical fields, they're 0. And now we have the exclusion principle. And yeah, so I go on and I waffle about that for a page or two. But that's as close as I can come to telling you why we have to have the exclusion principle and why we have, protons and nuclei and atoms. You can't have two fermions in the same state. So, I don't know, I'm out of breath. Ask a question. We got 5 minutes left. Oh, can't hear. You're not going to say anything. Okay, go ahead. Anybody say something. I'm tired of talking.
Is that the deepest proof for the exclusion principle that exists, or is there more layers to it?
No, I would say that's as deep as it goes. Yeah, I haven't seen anything deeper. Yeah, I think Pauli proposed it as a way to ensure the exclusion principle. I mean, you can ad hoc introduce it, say, okay, I'm going to require these fields to anti-commute because psi squared has to be 0. But this is actually a derivation. I've looked at every way I can think of to try to find an alternate way to get the signs right. But you're going to get non-conservation of everything comes out wrong if you don't have anti-commutation. We're going to do the Hamiltonian next, right? And the Hamiltonian comes out with a minus sign on the d dagger d part. You know, your energy is not positive definite without this anti-commutation relation. Then you look at charges, and you'll find that that particles and antiparticles have the same charge. You know, that can't be right. If you look at just the field, so you've got an annihilation of a particle coupled to a creation of an antiparticle. That conserves charge, right? It wouldn't conserve charge if you interchange d and d dagger, right? I mean, you look at this, you think, oh, well, you know, I could just call d dagger and d dagger d. That doesn't work, because in our original field, we've got d with what we call d dagger initially. If we change that d dagger to a d, that field would be annihilating a particle and annihilating an antiparticle. That does not conserve charge, right? So we've just let's see. Yeah, we'll see it more definitely. I mean, the effects of that when we start doing Feynman diagrams, and what happens is you get interaction terms that correspond to diagrams like something like this, where you've got a photon coming off, you've got say an electron coming in, and the particles coming in are an electron and a positron. The positron looks like an electron going out, and so you've conserved charge. But if that vertex were to annihilate a positron at the same time it annihilates the electron, now you end up with a positron going the wrong way, and the charge changes. So you see it clearly when you start writing the interaction terms. So a lot of things go wrong. Now, could we fix it another way? I don't see another way to do it. You need to be able to create a well-defined space of states. Right, and in order to do that, we need a well-defined vacuum state that relies on a positive definite Hamiltonian. And we don't get that unless we introduce the anti-commutation on the Ds. That's going to make the Hamiltonian, that's the next thing in the notes. Takes a while to work that out, but what you get when you straightforwardly calculate the Hamiltonian is B dagger, no, I've got a B where I should have it. I have a B dagger where I should have a D. But anyway, you get a B dagger B plus a, you work it out, you get a D of minus K, but you end up with a B dagger B minus DD dagger. So your normal ordering is going to interchange the D and the D dagger, but it's the exclusion principle that forces the plus sign on that D dagger D. So normal ordering without the anti-commutation would leave you with an indefinite Hamiltonian, which is worse than having infinite vacuum energy. You're actively creating negative energy then. So it fixes that. Then let's see, I look at symmetries. Do I look at charge conservation just yet? Okay, yeah, here's the charge conjugation operator. And once again, you get a B dagger B plus DD dagger. And you sort of want to say, oh, well, Q is H and H is Q, right? The charge is really the Hamiltonian and the Hamiltonian is really, but they're not, right? Those all come rigorously from Noether's theorem. Right, you look at your symmetries. You can you compute the conserved U1 charge, and that comes out like all positive. And you look at the translation invariance, and you get the conserved Hamiltonian, and the Hamiltonian comes out indefinite. And that is energy, that is not charge. So you can't just interchange what you call H and what you call Q. So yes, I would say this is as rigorous as it gets, and this is rigorous. You know, it's field theory is complicated. You know, there are lots of details to these calculations. It's getting dark. A new sound. Oh man, I got to catch up with the chat here. I'll catch up after I finish because we're running over. But whoa. We've hit rock bottom. Yeah.
Yeah, Lyle had said that in response to us. This was our deepest proof of the exclusion principle.
Yeah.
Bedrock.
Yeah, I think we've gotten there. Because of the complexity of everything else we're doing, you know, it's hard to know you've got a proof of something, right? But you know, that's why I took the time to identify all of those, you know, metrics in any dimension and see that those are those always have indefinite. That's always an indefinite metric. So you, the fact that it's VIVJ gives a minus Kronecker, you know, plays into this. You know, everywhere you introduce a sign, but you got to check that each of those things couldn't be any other way. This is the reason that I've solved carefully for the mode amplitudes classically, because I wondered, well, could there be some other thing you introduce to make the fields operators? But no, you can solve for the mode amplitudes in terms of the fields and just fixed stuff. And so it's got, those mode amplitudes have to become operators. Once you make those fields operators under all the integral signs and stuff, they're not going to become unoperators. So that's inescapable. The sign in the inner product is inescapable. The wrong sign on D dagger D, you can put it on B dagger B. You can have the B and B dagger have the wrong sign instead of the D and D dagger, but one of them is going to have the opposite sign from the other, and that's compelling. So a noose operator. Yeah, well, a toaster and a bath operator. How do we get to the toaster and bath operator?
Well, the joke had turned to rock bottom. And
yeah,
that reminded me of that. You've probably read it before. Opening of a statistical mechanics book from Goodstein.
Okay, so what happened? All right, the states of, yeah, and maybe I don't know this story.
It's a genuine first paragraph of the text.
So what happens?
There, and it's just very humorous is all.
Dies of a toaster in the bath?
No, that's probably where our conversation turned.
Okay, all right. So,
but now those 3 sentences quoted in that book are worth reading for sure.
Yeah. Okay. All right. Good to know. Yeah, that reminds me of who was it who died from eating a poisoned apple? I've just been seeing about that lately. Somebody, I don't know, was it Turing or somebody? Somebody always had an
self-inflicting. Yes, it was cyanide.
Anyway, back to D&D dagger. You could make B and B dagger have the minus sign and not D&D dagger, you know, with a slight, you know, put an I in front of everything, you can get that to happen. But, you know, that doesn't remove the problem. You still have one of them creating negative energy states. So, yeah, we have hit the train tracks on this one. Rock bottom. So anyway, we're out of time. I mean, I'm happy to stay all afternoon and chat, but yeah, I know some of you have to go. Yeah, like yeah, Eli has to take off. See you, Guillermo. Yeah.
I had a quick question, I guess, on,
yeah, question.
well, this is a more out of left field question. Is there any like reason that people use like Grassmann algebras these days anymore for this? Because you just mentioned the Dirac
This is a Grassmann algebra, right?
Yeah.
I mean, yeah, superfields. Oh, okay. Now I got to tell you about superfields. All right. Yes. Since you asked, let's here. Let me change the view so I'm not staring at myself there. Okay. So, oh gosh, yeah, superfields are so cool. But yeah, people started writing supersymmetry things, and they live in a place called superspace. Some of them do. Not all supersymmetric theories can be written in superspace, but well, the nice ones can. So what you do is you let your fields be functions of 4 space-time coordinates and 4 fermionic coordinates, like this. So 8 coordinates, and the property of these guys is that they anti-commute.
Oh, sorry. Wait, you're putting coordinates on the conjugate space and on the conjugate spin space and on the real spin space? Sorry, is that what you're doing here at the spaces?
No, we're introducing a what's called a superspace,
Yeah.
which has both bosonic and fermionic coordinates.
Oh, okay.
So the coordinates along a theta direction are anti-commuting numbers. So now we have to ask, what are anti-commuting numbers? And happily, Alice Rogers gives us an answer for that. Very nice paper looking at this. So introduce some Grassmann variables, right? J, eta, I. And so I and J are going to run from 1 up to some L, potentially infinity, which actually introduces all kinds of quirks into the whole thing. But just suppose we have some a priori anti-commuting objects, eta, and they're just going to form a basis for everything else. So then we take the free algebra of the etas. So we have a number, and then we have a linear combination of the etas, and then we have some anti-symmetric coefficients here. Probably a good idea to put a half on that, and so on, up to well, eventually you'll have an N1, N2 through NL, but you can't go higher than that because you're anti-symmetrizing everything. You'd have to repeat one to go higher, and that would be 0. So this gives you 2 kinds of numbers. So you take Z to be x plus theta, where x is the even sector.
Oh.
And theta is the odd sector.
Sure.
Odd and even. Now, even ones commute. Odd ones anti-commute. Two odd ones anti-commute. Everything commutes with the even ones. So this is how she defines coordinates. There are a large number of these things, right? We have, order of the reals, number of these things. And so now I can define a space where I take 4 of the commuting ones and I take 4 of the anti-commuting ones, which I denote this way. So a point in this 8-dimensional space looks like this.
Oh, and the bar, that's the bar.
It's a complex conjugate thing. It's a conjugate field. So if I take a conjugate, these guys turn into one another.
Yeah.
The reason for that is, in the Lie algebra of the Lorentz group, you have, if you introduce a complex unit, you can write two commuting SU2s for the Lorentz group. Now, actually, the group is not. The algebra splits into two just disjoint SU2s. The group does not. It's SO4 that literally splits into a product of two SU2s. But anyway, what you do then in supersymmetry, a supersymmetry that can be formulated on a superspace, is you have your fields defined on this superspace, and then you can expand it in a Taylor series of these guys, but that always truncates.
Yes.
So I can have a 0th order, and then I can have, well, hey, a spinor field. Everything is still a function of x.
Sure.
And its conjugate. And then I can have a vector because, let's see, if I take a polymatrix, sigma mu includes the identity as well as the 3 polymatrices.
Yes.
So we've got an A dot here, and we have theta A, theta bar A dot.
I'm sorry, why? It's contracted over. I'm sorry. AA dot.
Yeah,
Okay.
there's some here. So we have a vector field, we've got a scalar field, we've got a spinor field, and we keep going up. So let's see, we can have, let's see, what will this be? You can have a theta squared. I'll show you what that is in a minute with a theta A bar dot. Better make that a dot bar, and its conjugate, theta, or chi A, theta bar squared, theta A. And then finally, one more scalar, sigma of x, theta 1, theta 2, theta bar 1 dot, theta bar 2 dot, like that. And so what you
Sorry, why aren't those squared 0 in the first one?
show you.
Yeah.
Right, these are each in 2-dimensional spaces, so you have a 2-dimensional Levi-Civita, like this. And so what theta squared is defined as is epsilon. Theta A. It's just a shorthand way of writing it. Right?
Oh,
So
I see. Okay.
it's theta 1, theta 2. Okay.
I got you.
So what we've defined here is a super multiplet with a spinor field, a vector field, another spinor field, and another scalar field. And the supersymmetry transformations become supercoordinate transformations on this spinor space, for which, for the super ones, we introduce an anti-commuting parameter that lets us turn spinor stuff into vector stuff and vice versa. And so you actually get transformations between these fields.
Mm-hmm.
So those are accomplished with some what I call a Q operator, which
is it something like nilpotent when it's finite dimensional or something?
is
like,
what nilpotent.
This QA operator, like, I guess what I'm saying is like,
Yeah.
Because it seems like you couldn't go from a higher order to a lower order, right? If it's finite dimensional.
Yeah.
It seems like you couldn't go from the higher or end of the series. You couldn't get first order terms out of it, right?
Yeah. Although, what you do is, you can multiply by a theta, but you can also differentiate. So you've got this anti-commuting paper. DD, you have some DD theta stuff. And if you look up Berezon's papers from circa 1980, the people who, there's Berezon integration and Rogers did this nice definition with the etas and stuff, making all this rigorous. People have done sort of classical mechanics with supersymmetry, and you get nice electromagnetic relations and stuff. It's really pretty cool how it all works out. But these Qs basically generate fermionic transformations that can take you up or down.
Yeah.
So at the same time, psi picks up a little bit of phi, phi picks up a little bit of psi. It goes both ways. Yeah, integration looks like differentiation and vice versa with these numbers. It's really very cool. Haven't looked at it in a while, but it's really quite funky. But these Qs, these guys satisfy anti-commutation relations. And what you have is a sigma A B dot with a translation generator. So what happens in supersymmetry is for the fermionic transformations corresponding to non-trivial superspace coordinate transformations, you have anti-commuting generators that give you translation. And what that means, if you look at the Jacobi identity for this, is that the Qs commute with p squared. Follows from this in the Jacobi, the super Jacobi. Now, what that means is that doing a transformation between these fields does not change the mass. So super multiplets of particles all have to have the same mass. And that's why supersymmetry is running into such a dilemma currently. For every superparticle, for every particle you see, you expect to see a superpartner of the same mass, and we don't see any, which is why people talk about broken supersymmetry. So what people think is there's some high mass scale, say around the LHC level, where the symmetry has been broken and half of every supermultiplet given very high masses, and there's every superpartner, so that one of every pair of matched particles is actually of very high mass. And what you expect, if that's the right scenario, is that there should be a lightest supersymmetric partner at some point very soon, if those theories are right. So you don't know if it's the selectron, the scalar partner of the electron, or the photino, the fermionic partner of the photon, or some other pairing, but there's got to be a lightest one, and you should see it very soon, or else change your models, change your supersymmetric models.
Where does that breaking effect come? Is it this Q operator where they introduced this symmetry breaking, or like does it end up having
it's probably some sort of a, I'm not sure, I haven't looked at those models, but it's probably something like like a Higgs mechanism or something, where you have a symmetry, but you've got some field that at low energy seems to break the symmetry. I don't know. Have we talked about how the Higgs works?
I've seen that one a couple times, but a general path towards symmetry breaking, I don't know if I've seen symmetry breaking in general. Does it that your differential operator starts becoming I guess it's non-covariant is the word, the Babel word to use, but is that where the
No, that's the whole point of the Higgs mechanism, is it still preserves the symmetry. It's just that at low energy, the field falls into well, they call it spontaneous symmetry breaking, but it's not actually breaking the symmetry, right?
Yeah.
You've got.
I think I've seen that where you add the fourth order field to the Klein-Gordon. I've seen that version of it, and then.
Yeah, and we'll probably do that in a few weeks to as a
Cool.
simple quantum field theory, right? But, if you've got this covariant derivative of the complex Higgs, so you have something like this in the action.
Yeah.
And, there's also a coupling of the Higgs, maybe to say, oh gosh, what is it? To some spinner, psi or psi, or something like this maybe. And what happens is you also have a quadratic and a mass term for the Higgs. But as a scalar, these don't break the SU2 symmetry. These are this is an SU2 scalar here.
Right.
This is an SU2 scalar. All of this.
Right.
So, and I forget what this coupling looks like, but the point is, that's a Mexican hat potential, right? That potential looks sort of like this, and at low energy, this field is going to fall into the bottom of the well, the potential well. And so while the Lagrangian as a whole has the symmetry, low energy solutions are going to introduce this large constant number here that in a term like this looks like it's giving this field a mass because you've just got a constant here.
Yeah. Okay.
Right.
So it's where we're starting from a symmetric Lagrangian and then taking some limit or some special variation and then noting.
Yeah. So you look at low energy, you see, this field takes an essentially constant value of some sort that looks as if it's a mass for this term, but really there's, at high energy, all the symmetry is restored.
And so then for like these super symmetry fields, they're writing down the action just the same and then taking a limit, and the subtlety is trying to find sectors that look like the masses you'd expect. Is that?
Yeah. Yeah. So this is called spontaneous symmetry breaking. The symmetry is not evident, even though it's really ultimately still there. The fields fall into, low energy values where the symmetry is broken. So it could be a mechanism of that sort that gives a large mass to the superpartners, or it could be that I would suspect that that's the kind of model that people are introducing.
Sure. And then all the subtlety becomes how you take that limit, I guess, because who knows how it trickles from the original action to an actual limiting form where you're calculating irreducible masses, right? I mean.
Yeah. So at high energy, the symmetry is restored and the masses go away.
Mm-hmm.
If your energy is much higher than that effective mass, then you don't see that mass at all.
Cool. Okay.
So the extremely high energy picture is a lot different than what can happen at low energy. So that's one mechanism that could explain why we don't see superpartners. But there are limits on how big that mass can be just from other constraints, and we're getting pretty close to those limits. There is a way within conformal gauging to produce supermultiplets that don't have the same mass. Ask Eli about that. Do a Zoom with Eli and try and get him to, because he's supposed to be working on that. We've got a project outlined, but ask him to explain to you how it could be the case that supersymmetry at low energy is not broken.
Cool.
Yeah.
So does the Dirac, does the Pauli exclusion principle then kind of only hold? I mean, it's a low energy theorem, right? Because it holds when the Dirac field is the leading order term. So in some general interaction scheme, is the Pauli exclusion principle is a low order, and is that like, is that just
that's at any order? No,
well,
that's,
I guess Well, like if you smash two electrons fast enough together, does the state of a stationary electron mean anything, or does it become like a plasma soup? I guess would be my question.
Oh, well, yeah, people smash things together at high energy. Actually, the highest energies you get are when you take heavy nuclei and cyclotrons, because cyclotrons accelerate each proton in a heavy nucleus, and you can put a lot more energy in one place. So if you collide these heavy nuclei, you get a quark plasma.
Yeah, but electrons are fundamental. So
yeah, oh yeah. So what happens there? Yeah, we have seen no evidence for structure of an electron. People look, of course.
Of course.
Yeah, but yeah, there's no evidence that there's any substructure to an electron or a quark. People build theories and predict what you would see if there were structure there, but there's no evidence for it.
So do all the W vector, those are vector bosons, right?
That's right.
So do those come in clearer in this superalgebra picture, or?
Okay, it depends on what superalgebra you're looking at. So so what people looked at, well, superstring theory, of course, is a 10-dimensional, well, you get an effective field theory, but people were looking at supergravity theories. What you want in expanding your superfield, you can write down a vector superfield where there's an additional vector index on each of these things, and this highest order field in the middle would become a spin 2 field. But you don't want to go higher than that because we don't see anything with higher spin than the spin 2 of the graviton. So, but you can have a supergravity theory where part of your supermultiplet is the graviton. And there's okay, I'm going the wrong direction here. There is room in these theories for internal symmetries. So you're not restricted to just one kind of supersymmetry. You can have up to 8 different kinds of Q. So you can have, it's called N=8 supersymmetry, capital N. So you can have a system that has 8 distinct supersymmetries. So each of those has a square to 0, but you can have 8 completely different ones, completely different fermionic transformations with like an SU8 or an SO8 symmetry connecting them.
So is that Yang-Mills theory for each?
That would be a Yang-Mills. So if you have an internal symmetry like that, so suppose I have 3 different fermionic fields, each with a Dirac action, right? If they all have the same mass, say 0 is convenient, then an SU3 rotation among the 3 fields leaves that action invariant, right? So that's called an internal SU3, and you could gauge that and produce the strong interaction. So
about the weak interaction?
For the weak interaction, you need an SU2 cross U1. Well, weak you can do with just SU2. Electroweak, you start with SU2 cross U1.
So like, I mean, is electroweak theory just quantizing a Dirac field coupled to E and M? Is that?
No, electroweak, you're coupling, let me think now. Your Dirac fields couple to SU2 cross U1 gauge fields. So you have something like this. Let's become green here.
So it's just a gauge theory on Dirac fields?
Yeah. So
okay.
So we've got psi bar I d slash minus m psi, but now we introduce multiple fields here, and now this has, say, SU2 cross U1 symmetry. Right, so that, well, that could act on, yeah, you could actually do that with 2x2 matrices. So you have an identity for the U1 and the SU2 as Pauli matrices. So you could do it with actually just two spinners. But now you make that local, so this becomes a covariant derivative. And the covariant derivative of psi is going to be something like, okay, you have a partial derivative, and then you have a U1 gauge field like this, and then you have an SU2 gauge field. That's not going to be the photon, though. Let's call it something else. Then you have three SU2 gauge fields that are going to be something like, let me think. Let's see, what do we want to call these? Well, let's call them W dot sigma. IJ acting on psi j. So these all have an I on them like this. So, something like that. So your connection is an SU2 cross U1 valued connection. Right? And then you've introduced four vector fields, 3 here and 1 here. And what you find is that a certain combination of B mu plus the diagonal one here, W3 mu, is the photon. And well, the opposite combination, the orthogonal combination, is the Z naught. And then the off diagonal ones here are the W plus and minus.
Oh, brilliant.
So they're all vector fields.
This is almost looking like the spin up and down sectors that we just did, except we've got a row sector too, right? These are matrices as opposed to a spinner. Operators.
Yeah. This is a third independent space, right? So we're in space-time, we're in some 4-dimensional spinner space, and now we're in this 2-dimensional SU2 space of some sort, right? So there are 3 independent sets of indices going on here if you want to put in all the indices.
Okay, yeah. Okay, so okay, that makes that I can get my head around that where we're at though. So it's just a gauged Dirac field. Oh, cool.
Yeah, that's right. Yeah, so yeah, you pretty much start with a bunch of Dirac fields, right? And you introduce every sort of interaction you can think of, and you look and see which ones actually exist. Well, this one exists. And yeah, so when people talk about SU2 cross U1, that is not the weak interaction. That's not the electromagnetic interaction. It's actually this combination of the diagonal element here with this one. One combination gives the photon, one combination gives the Z naught. So it's a non-trivial unification. And there's like sines and cosines here, and you've introduced an angle, a mixing angle, the Weinberg mixing angle.
Is there like something similar you can do in like, now I'm just trying to make a simple example. Like if you could you do like a similar gauge theory with like some type of polarization field with intensity field? Like if you have maybe polarization is a bad because that's the U1 I think would be here. Actually, I don't know. Is polarization SU2? You might actually.
Well, polarization? No. Well, normal electromagnetic polarization. Well, we're going to quantize E and M after we finish Dirac. It's just a vector. Those are just vector directions. So yeah, you have a lot of gauge freedom with a U1 gauge field. The vector potential. You can impose both the Coulomb gauge and the Dirac gauge, so that there are only actually 2 independent fields, not 4. And let's see, those you span with a real two-dimensional vector, the polarization vector. So yeah, that's not a unitary group doing that. It's just it's just an SO2 symmetry for the polarization.
I'm just trying to think of a simple system that I can see the picture of why things are decaying into things, especially as this gauge picture. But now I want to see a simple system
Yeah.
that I can say, oh, that's what the W plus is. But okay, sorry.
Yeah, let's see. So yeah, the W plus, W plus and minus are certain combinations of the off diagonal generators here.
So how does well, I mean, maybe we'll get into this. We will with the interaction picture, but how does this, because from what I've seen is we have a fermionic field that all of a sudden a boson is jumping out, and that's maybe because I haven't seen a gauge theory on a spin field yet, but is that a property of these where
So that's what we're looking at here. So if you write this out, you write out this covariant derivative, right? And what you have is psi bar id slash minus m psi, plus now these extra terms from the covariant derivative. So you're going to have psi I bar with, say, it's going to become a b slash psi. So, and then other things with the w's. But okay, look at what this is. This involves three fields, right? We have like antiparticle field. You have a gamma matrix. Now you have some kind of a vector field, and you've got, let's see, I guess let's see. So let's just do U1. Here, for just U1, you would have a term like this. Now, when we do the path integral perturbation, what we're going to do, we're going to sum over all field configurations minus I over H bar, and then we've got the action up here, but we're going to write that as the basic field action for a free Dirac field times or H bar with an interaction term here. That's this guy, right, from here.
Sure.
And this one, we can solve that completely. We pretty much just have. But this one, you expand in a Taylor series. And, you write this with a Hamiltonian and stuff, but then higher order terms. So the way you end up handling this in Feynman diagrams, you can show term by term that a transition amplitude dependent upon this can be approximated by saying, at some point, this a mu is emitted. So, this is an electron comes in, this is a positron comes in or an electron goes out. And you end up with something like this. Well, that's first order in perturbation theory. And you should say, actually, I'm going to go to quadratic order here. You could have two photons come off, something like that, right? Each time you have a vertex, you're looking at some corresponding order in perturbation theory. So if you have some scattering problem like this, you've got 4 vertices, you're keeping up the 4th order here. Well, 4th order, and you need 4 vertices. So you'll need this. You need a term like this 4 times.
Yeah. And then if you let's see if I can do can I do math on the fly? If you then take the variation of this action with these interaction terms, then are just going to contribute to each Euler-Lagrange equation, right? So they'll just look like source terms on the right side.
Oh, absolutely, yeah.
Oh, so that's exactly why we associate.
Yeah. So this this gives rise to the U1 current. So the source that this introduced, if I vary A, right, that's going to give a source for the Maxwell equations. And the source is going to be something like psi bar gamma mu psi. Well, that's the U1 nether current from the Dirac action, from the original action. So yeah, it ties all very tightly together with the classical picture of what's happening. So instead of having some phenomenological current J as the source for your Maxwell equations, the only sources are things that come directly out of the field theory from the gauge couplings.
Okay, and then the higher order, the W terms, do those? So okay, so one, do those only exist because we have more than one space dimension? Is there a reduction that happens if, or is it just, no, it's happening because of the SU2 cross U1.
Yeah,
that's where we're getting
SU2. Yeah, the dimension of space-time is irrelevant. That's the range of that index there, right? The number of fields here is different, right?
Yeah, that's the gauge. B is like the gauge vector, right? Is like a gauge vector. Is that?
Yeah.
And then the W is
this B or that A or the W I had. Those are gauge vectors. Vector boson.
Well, I guess my question was, the W something like a gauge tensor then? Like it was being multiplied into a vector. This SU2 gauging, I guess we'll see it in a second, but
no, the SU2.
I'm sorry, I'm being stupid.
They are all vectors, right? So
with just the symmetries of SU2, the gauge field has
with just SU2.
Okay.
You have a space-time covariant derivative of your field. So you have a partial, but then your gauge field, right? You have two spinor fields, and they're coupled because this gauge vector, let's call it B, is a Lie algebra valued. Let's write it correctly this way. A connection is a Lie algebra valued 2 form, right? So the Lie algebra value on these guys can be accomplished by contracting them with the Pauli matrices. So you introduce 3 of these fields and dot them into the 3 Pauli matrices. And so all of this together is a Lie algebra valued 1 form. It's a 1 form on space-time, and it's Lie algebra valued because it makes an SU2 Lie algebra connection actually mix the fields.
So Lie algebra valued 1.
So what a connection does, when I move from this point to this point in space-time, I may be changing my basis or interacting with some other field that does some internal, in this case, SU2 rotation of my fields as I move around the manifold. So it's an SU2 fiber bundle. And I need a connection that tells me how this fiber relates to that fiber.
Mm-hmm.
So my fields are, let me see.
Displaced by an SU2 invariant.
Yeah, that's right. Yeah. So
okay, yes.
This is now SU2 covariant. Right?
Okay, so
yeah.
Okay.
So the covariance property tells me that if I do an SU2 group transformation on psi, this is going to be some GIJ psi j on the internal index. So if I do that on psi, and at the same time I change B to B tilde, and what that means is GB G inverse minus DG G inverse. So B transforms that way. Then d mu psi, so this is psi tilde, is G acting on psi. So d tilde acting on psi tilde is just G acting on d psi. That's what I mean by covariance.
Yeah.
And this form of transformation of any gauge field, general relativity, same thing, will accomplish that covariance.
Yeah. Okay. Yep. This is this.
Okay.
Okay.
And yeah, you know, we'll be writing this in the book soon.
Yeah. It's just in the pudding is that you just know that you have SU2 cross U1. So that's what we'll see in a second as you break it down, and then you get.
Yeah.
Okay.
So you know what you do is you write down like everything, every interaction you could within the formalism, and then you go out and test whether you really see them. And what we see is a left-right asymmetric SU2 interaction for the weak interaction. There's actually, it's not just
because of the derivative, the dg inverse.
It's not just let's see, right, psi bar, you know, some field slash psi. There's actually a 1 minus gamma 5 in here. And that makes it the left and right-handed interactions are different for the weak interaction.
Oh, fascinating.
But
Okay,
yeah, but you know, that was discovered back in the 50s or 60s, was it?
Mm-hmm.
Yeah, quite a.
And in general, it's not as easy. In general, it's not as easy to break what your gauge, like visualize what your field is based on what your gauge group is. Like if you break up your gauge group into products, it's not easy to visualize your field because there's that mixing term where your DG with G inverse. Is that right? Where your connection is non-trivial.
Yeah, well, actually, that works in your favor because you're allowed to choose G any way you like because you've written a theory that's G invariant. You can do any say SU2 transformation you like, and that can simplify your fields. People do this with the Higgs all the time, where all right, SU2, you've got 3 gauge degrees of freedom, right? It's a 3-dimensional Lie group. So I can do all of those transformations. Well, okay, the Higgs is a complex scalar field. That means it's got 4 degrees of freedom. I can use the gauge freedom to reduce it to just 1 degree of freedom. And I do. You know, that just makes it a lot easier to work with. So in many ways, gauge is your friend. You know, it's like the argument I was giving earlier today. What was it I was saying was, I was saying some argument was really easy if you just use the invariance. Oh yeah. You know, computing these inner products for the spinners is trivial in the rest frame of the particle, right? Because in that rest frame, hey, oh look, they're all orthonormal, right? What's your metric? Okay, 2 or plus, 2 or minus, you're done. And that's true. That's absolutely true. You know, that's how you use gauge freedom. So so all of these properties, inner products of the U's and the V's are completely trivial if you do them in the rest frame and then imagine boosting to any other frame later. It's not going to change any invariant expression. So if you can write the inner product invariantly, you're done.
Mm-hmm.
Well, you know, the same is true with this internal gauge symmetry. It can be your friend in a lot of situations.
Okay. Yeah. Okay. Yeah. This makes sense, but I'll just have to get pen on paper.
Oh, for sure. And we're going to cover this, I hope, you know, this summer, if not this spring. Yeah, these have been really good questions, Alex. So I've kept the recording going. I hope you don't mind. But yeah, this is, you know, the others might want to listen to this at some point. But
Sure.
I'll stop.
I'm used to embarrassing myself, so I don't mind.